guys, it's Stella. Welcome to the Planck's Law tutorial.
And it's Lizzie. We're here to show you, to shed some light on the nature of light. It's Lizzie.
All right, so you heard some goofy sophomores there.
Senior, what? She's a junior.
All right, pardon that. I won't edit this part out. Okay, so yes, we are going to pick up our tutorial on the discussion of nature of light. If you remember in class, we were talking that we weren't sure if it was a particle or a wave until the end of the 19th century. We were very, very sure it was a wave. There were a few cracks in that idea, and we're going to look at those cracks. And those cracks then lead to ultimately an interesting way of interpreting light. So the focus of this tutorial, I'm going to keep it brief. I think it'll be brief. Will be on Planck's law, and it's centered on this problem. Okay, so I'm going to put, even though the black body radiation isn't Planck's law, the solution is. Okay, so let's just put that Max Planck. Okay, so the problem that Planck undertook was he could not explain the classical distribution of wavelengths for a particular temperature body as an EM wave. Okay, just couldn't do it. The best minds of the time, Rayleigh, Jean, Planck, tried, and they could not reproduce the curves. If you look at this particular graph, that's a theoretical graph. That's usually called, that's a classic theory. You can barely read it here. And this is called the Violet Catastrophe, because at the low wavelengths, when we start to get to the violet part of the spectrum, this thing went to infinity. And that clearly was not the case. So through a little bit of desperation, good luck, and hard work, I mean, Planck was a very, very intelligent physicist. He came up with a solution that started the quantum revolution. So we got to, again, think of what was the known at light. So at the time, the idea of, let's take red light here. Red light was a continuous electromagnetic wave. Okay, something like that. So if I'm shining a laser for a brief period of time, I might get this length of wave train where the amplitude is goes towards the energy, right? It's because it's red, it's a particular frequency, and it has a corresponding wavelength and a speed. So that's your classical idea of a wave. The solution to the black body issue, which Planck gave us, was completely opposite, in a very real sense, revolutionary from a physics standpoint. He said, in order to explain it, you must treat light as tiny bundles of pure energy called quanta. Okay? Nowadays, we call the particle of light a photon. All right? And we're familiar with that term. So what exactly is a photon? So in one way, we can, instead of this continuous wave, he's saying that if you shine a red laser for a small amount of time, what you're going to get are little bundles of pure energy. So not a continuous wave. And there's no amplitude to these bundles. There's an energy, and he came up, and this is very important, with an equation to quantify the energy. Okay? And this is what we're really, people say this can't be right. He said it depends. The amount of energy of each little photon is dependent on the frequency. Yeah, you heard me right. Frequency. Or, put another way, the wavelength. In no classical wave does the energy depend on frequency. Energy depends on the amplitude. And for light, that would be brightness. And what Planck is basically saying is, you can think of the brightness of a light not as an amplitude of a wave, but simply the number of photons. That's the overall energy. But the individual packets of energy depend on the wavelength. And that's revolutionary. And the equation he developed from this, that came out of a solution to black body, was amazingly simple. It says the energy of any photon is simply equal to a number, h, multiplied by its frequency. Okay, or you could write that h, when you can take out frequency and substitute in the wave equation, and so I'll solve that for lambda, and you could say it's hc over lambda. All right, so that's Planck's law right there in a nutshell. It's a little bit more complicated than that, but we can reduce it down to that. And if you want the total energy, not that we normally calculate that, but if you're wondering, energy total would simply be N times HF, where N is simply the number of photons. Okay, so let's talk about that H, because H is one of the most important numbers in all physics. It's right up there with big G and little c, the speed of light. It represents Planck's constant. Okay, and of course it's in your reference tables, but I'll give you the value here. It's 6.63 times 10 to the negative 34 joule seconds. All right. What stands out about this value is the negative 34. It's exceedingly tiny. And in fact, we're going to do a lab where we can derive that. We've learned already we can derive very small values by making other measurements. We've derived the mass of an electron, which is 10 to the negative 31. But still, it's tiny. So what the implication of that is that if we go back to these photons, each photon is going to have an energy equal to h times, or the frequency times h. So that's going to tell you each photon is a teeny tiny amount of energy. And that's not contradictory, but if you got a bright light where you got gazillions of photons, then you can add all those tiny energies up to get a more macroscopic amount of energy on the order of joules or fractions of a joule. We'll do some problems with that later. All right, this star we'll come to later. I'll show you in class tomorrow. So let's finish up. We'll do some problems with Planck's law. Okay, so example, what is the photon energy of yellow light if the typical frequency is 5 times 10 to the 14th hertz? Okay, so that's a pretty easy problem. Energy of the photon is HF, which is going to be 6.63 times 10 to the negative 34 joule seconds. And by the way, a joule second is an interesting idea. That's called action, but we're not going to really get into that too much. Okay, so I'm just typing this in my calculator right now. And then we're simply going to multiply it by that frequency. So 5.10 times 10 to the 14th hertz. Whoops. And we multiply it by that. Whoops. Oh, crud. Okay, sorry for that delay. We get 3.4 times 10 to the negative 19th joules. All right, so it's a tiny amount of energy. Interesting that the exponent is negative 19 because we've seen that before with charges of electrons or protons. And that's not a coincidence, but it's something we'll talk about later. Since this is such a tiny energy, we want to express that in electron volts. So it's been a long time since we've talked about electron volt. So this is a good time to remind you of something that you should know. In your reference tables, we see that an electron volt is 1.6 times 10 to the negative 19th joules. And that's not a coincidence. That comes from the definition of electron volt, which is the elementary charge multiplied by a certain voltage, 1 volt. So 1 elementary charge across 1 volt is a definition of electron volt. And if you take the elementary charge, which is 1.6 times 10 to the negative 19 coulombs, multiply it by 1 joule per coulomb, you get this number here. Anyway, so if I want the number of electron volts, it's going to be 3.4 times 10 to the negative 19th joules divided by 1.6 times 10 to the negative 19th joules per electron volt, and that's essentially 2 eV. Okay, so the energy of a typical photon, yellow is more energetic than red, is still pretty small. Now, we could turn this around and say, what if we wanted to make 1 joule of energy? How many photons would we need? And we're talking yellow light once again. So now we can use the idea that the total energy is equal to N HF, or N of the N times the energy of 1 photon. So our N would be our total energy, 1.0 divided by energy of 1 photon. And we got to do that in joules. So that's going to be 3.4 times 10 to the negative 19th. And I'm going to guess, I don't feel like getting the calculator out, okay, but I'm pretty sure I can be within the ballpark. I'm going to say this is going to be about 3 times 10 to the 18th photons. All right, so you need a million trillion or 3 million trillion photons in order to get just measly 1 joule of energy. But that's not the point, okay? The revolutionary aspect of Planck's idea, and this is where I'm going to leave off, was that you do not control, and I didn't emphasize this before, you cannot, at least in this circumstance, treat light as a continuous wave. It comes in discrete amounts. And that discrete part is going to be a common theme in modern physics. Discrete means you can only have this amount or another amount. There's no between. We've seen that with charge. Now we're seeing it for the first time in the history of physics with energy. It was always thought energy could take on whatever value. Planck is showing that no, for light it can only take on discrete amounts, even though the difference between one and the next is an extremely small number, 10 to the negative 34, it's still very real, especially on the scale of the atom and the nucleus, and it even shows up to explain how warm bodies or hot bodies emit radiation, and that was why it was so important. Okay, so in class, we will pick up where we left off with a related phenomenon, the photoelectric effect, and then there's a lot more details in that.